Okay, welcome back. The last lab that we've done, the constant linear motion lab, both parts 1 and 2, have been really important because part 1 showed us how to define speed and velocity. Okay? If we have a distance versus time graph, we know the slope of that is the average speed of the object. Then we went and we talked about the difference between speed and velocity, and then we went and talked about the difference between average speed or velocity and instantaneous speed or velocity. Average speed or velocity we can find from the graph by looking at the slope of the best fit line. Instantaneous speed or velocities we can find by using the midpoint method, which is kind of like finding a mini slope between, for a certain data point, you look at the point before it and the point after it, and you find the slope of an imaginary line between those 2 points. That will tell us the instantaneous speed or velocity. So let's just summarize that. On our lab, the data that we actually took, what we actually measured, was distance versus time data. Very basic. You could have done that years ago. We used it to make a graph, the slope of which told us the average speed. Then, to find the instantaneous speed, we used the midpoint method, which involves us finding the slope between the point before and point after a midpoint. And then what do we do with that? We used it to make a graph of instantaneous speed versus time. That's what we've done so far. You just got done making that graph, okay? And on that graph, you were asked to find the slope of the instantaneous speed versus time graph. And if you think about the units of that slope, that should be, let's see, on the y-axis we're centimeters per second, and on the x-axis we're seconds, so the units are centimeters per second divided by seconds. Now remember a little trick from math. If you ever have a complex fraction like this, a fraction within a fraction, what you can do instead of dividing a fraction by another fraction, you do this. You take the fraction in the numerator, centimeters per second, and instead you multiply by the reciprocal of the denominator. The reciprocal of seconds would be 1 over seconds. So this gives me centimeters times 1 on top over seconds squared on the bottom, centimeters per second squared. And this is actually going to be very important because it clues us into what the slope means. On this graph that we made, and any other velocity or speed versus time graph, the slope is very literally a change in speed or velocity over a change in time. Okay? A change in speed over time, or a change in velocity over time, depending on which one we care about at the moment. So a change in velocity over time, what is it called when your velocity changes? Okay, what are you doing? You are accelerating. This is actually the definition of acceleration. Okay? By the way, acceleration is a vector, so it has direction. But this is very important. The slope of a velocity versus time graph tells you the acceleration of the object, okay? Not every slope tells you speed. That's specifically only for a distance versus time graph. On a velocity versus time graph, the slope tells you the acceleration, or speed versus time graph, whatever you want to call it, okay? I don't mean to imply that speed and velocity are the same, because they're not, but in a lot of cases we can use them fairly interchangeably. So the idea is that the acceleration of an object is equal to the change in its velocity over a change in time. On the reference tables, that is written like this, because this equation is right in the reference tables. On the back, you can see here's our average speed equation. V hat equals d over t, and you can see that V hat, you've got all the listings down here. V hat is average velocity or average speed. D is either displacement or distance, and t is time. The second equation, the one we're looking at right now, is A equals delta V over t. A is acceleration. The delta symbol just means change. V, again, average velocity or average speed. In this case, technically it's average velocity. And t is a time interval. Okay? Notice it says time interval, not just any time, it's an interval of time, some period of time, okay? Not just one particular instance. So the equation is A equals delta V over T. And that is the equation in your reference tables. That is the definition of acceleration, a change in velocity over some time interval. I do want to show you one other equation you can get from this, and it has to do with the fact that this delta means change. Anytime we have this delta, what it really means is final minus initial. The final amount of something minus the initial amount of something. So in this case, it would be A equals VF, the final velocity, minus the initial velocity over time. But I can rearrange this, can't I? If I multiply both sides by t, if I do this, that'll get rid of these t's, and I'm left with VF minus VI equals A times t. And then if I add VI to both sides, I end up with this. VF equals VI plus AT. And this is also in the reference tables. Okay, this is the third equation down from the top. So this equation and this equation are actually exactly the same. They're just written slightly differently. Usually people end up using this one a little bit more, but both of them are valid. Okay? And again, remember that, well, actually not again. This equation, you'll hear me refer to it as this. Someone came up with it my first year of teaching. They saw the FIAT and they just started calling this the fiat equation. Like I said, someone came up with that a long time ago. It's stuck in my head now. It's stuck in every other person that I've taught's head now. So you can refer to it as the fiat equation and we'll all know what you're talking about. But no one else calls it that. So if you go out in the wide world and you start calling it the fiat equation, everyone's going to look at you funny. Okay? Anyways, this is the definition of acceleration. This is a slight rearrangement. I also like to call this one the first kinematics equation. We'll get to what the second and third kinematics equations are later on. So we just got two new equations that we can use. It's time to practice with them. Our first example says a ball accelerates at a constant rate as it rolls down a ramp from rest. After 5 seconds, the ball is moving at 3.5 meters per second. What is its average acceleration? So let's talk about what we know so far. It says after 5 seconds, that means the time interval that we're dealing with is 5 seconds. After 5 seconds, the ball is moving at 3.5 meters per second. Now that's got to be a speed because it's listed in meters per second, but is it the change in speed? Is it a final speed? Is it an initial speed? What is it? Okay. Well, we can tell what it is. It's definitely not a change in speed. Well, it's not necessarily a change in speed, but we are told there's two little words here that are very important. It says from rest. From rest means something was not moving when this time period started. That would be like saying the initial velocity is 0 meters per second. Okay, so whenever you see the word from rest, that means the initial velocity is 0. Therefore, if it started at rest and then it was moving 3.5 meters per second, I would say that the final velocity is 3.5 meters per second. And what we're looking for is the acceleration. It says average acceleration, but that's what this equation tells us. Technically, we should have a little hat over this, but we don't. That's fine. That is not known. I look through my equations and I say, okay, I'm going to use the fiat equation. You could also use this equation. That's absolutely fine. What you would have to, well, I'll show you in a sec. I'll show you that one in a sec. VF equals VI plus AT. Now, here's a little trick. Since VI is 0, I don't have to plug in 0 for this one, but you have to do it in a very special way. If you know that something is 0, you can cross it off in the equation like this, okay? Put a line with an arrow through it, and then just write 0 up top. If you don't write 0, I will not give you credit for doing this. All right, you have to write a 0 up here. If you just cross it off, it looks like you made a mistake with your equation and you're trying to fix it, okay? If something is 0, you cross the term off with a line through it and you write 0 above. And that way you don't, I'm not going to make you write 0 meters per second again. All right? Final velocity, 3.5 meters per second, equals A, what we're looking for, multiplied by 5 seconds. I divide both sides by 5 seconds, and I get 0.7, and the units would be meters per second squared. Meters per second divided by another second, or meters per second squared. Now, could I use that other equation? Absolutely. I could have done this. A equals delta V over T. Then what I would ask you to do if you're going to use this equation is anytime you have a delta V, you can't just write out what the difference in speeds is. You have to write VF minus VI, so I know exactly what you're plugging in over T. That way I would get, let's see, this would be 0, 3.5 meters per second over 5 seconds. You get the exact same thing. Okay. Let's look at another example. A car moving at 30 meters per second on a country road enters the suburbs and slows down to a speed of 12 meters per second over a period of 10 seconds. What is its average acceleration? Well, I know that it was moving at 30 meters per second, then it slowed down to 12. So that tells me that my initial velocity is 30 meters per second. My final velocity is 12 meters per second. And it took 10 seconds to do this. Again, the question is, what is the acceleration? I can use the Fiat equation again. VF equals VI plus AT. There's nothing to cancel out this time. There's no zeros. VF is 12. VI is 30 meters per second plus A multiplied by 10 seconds. Now, you can show all of your math steps on here, and I encourage most of you to show your math steps so that you can get everything squared away and that you're not making any mistakes. There's no rule that says you have to show the math steps. You have to show the plugging in, and then you have to write the first, so you write the equation first, you have to show the plugging in, then you can write your final answer. You can do the math steps if you want, and I encourage you to do so, but for me, I know that this is going to be 12 minus 30 divided by 10, and I end up with 1.8 meters per second squared equals A. That's my answer. So a couple things to notice here. Again, I would encourage showing your math until you get very comfortable. Notice that I get a negative acceleration. That's kind of weird. What does that mean? Okay. Notice that the negative acceleration in this question showed up when we had positive velocities. But notice what happened to the velocity. The velocity went down as we went from initial to final. This is a slowing down of the car. Meanwhile, in this case, we had a positive acceleration and the velocity increased, went from 0 to 3.5. So, here's a little rule. If you have an object that is moving forward, then if it has positive acceleration, the object speeds up. It moves faster and faster. If you have negative acceleration, then it slows down. Okay? Another way of thinking about this is if the acceleration and the velocity have the same sign out in front, that means both positive, then the object speeds up. If the velocity and the acceleration have different signs, one is positive, one is negative, that means the object slows down. It's starting to come to a stop. That's important to remember. We're going to go to another example now. A ball is dropped from rest from the window of the classroom, and it accelerates toward the ground at a rate of 9 meters per second squared. If it takes 2.1 seconds for the ball to hit the ground, how fast was the ball moving right before it hit the ground? Well, it says the ball was dropped from rest, so that means VI is 0 meters per second. You might be tempted to say that the final speed is also 0, but we want the speed right before it hit the ground. It's not in contact with the ground yet. We want how fast it was moving right before it hit the ground, and you'll see that that's the case in many physics problems. You're almost never going to say, like if something's asking how fast it's going at the ground, you're not going to write 0 because it's on the ground. They want the speed right before it hits the ground. So that's what we're looking for, VF, question mark. The acceleration, it says, is 9 meters per second squared, and the time is 2.1 seconds. We use our Fiat equation, VF equals VI plus AT. The initial speed was 0. Final speed is what we're looking for. The acceleration is 9 meters per second squared, and the time is 2.1 seconds. 9 times 2.1 is 18.9 meters per second. Now, I do want to make the note that this final velocity of 18.9 meters per second, what direction is that in? Well, if the object is falling, that means the velocity must have been pointing downward. And since the object clearly sped up from 0 to 18.9, that means that acceleration was downward as well. Okay? We wrote positive, and as we go forward in this class, you're going to have to start to deal with directions of certain vectors. It is usually up to you what direction is going to get a positive sign in front of it and what direction is going to get a negative sign in front of it. We're going to deal with that in a few more videos, or maybe even a problem later on, but that's something that you're going to have to deal with. But it is up to you, which is nice. Next example. A skier gets to the top of a hill moving at a speed of 6 meters per second. So that sounds like an initial velocity to me. 6 meters per second. While moving down the hill, the skier experiences a constant acceleration of 1.3 meters per second squared for 11 seconds. So the acceleration is 1.3 meters per second squared. The time is 11 seconds. Notice that the skier, we can probably say safely, he's moving forward, and the velocity and the acceleration have the same sign. They're both positive. This means we should expect the skier to be speeding up. What is the skier's speed at the end of this time period when he reaches the bottom of the hill? In other words, what's his final velocity? Nothing to cancel out here. We just do 6 meters per second plus 1.3 meters per second squared times, oh my gosh, I put a squared in there. I'm sorry, I shouldn't have done that. Thinking of another equation, times 11 seconds. 1.3 times 11 plus 6, the final velocity is 20.3 meters per second. And see, the skier did speed up. This next question has 3 different parts to it. Okay, this is a little complex. A new roller coaster has a section where riders move at a high speed up a steep incline, they stop, and then go back down the incline backward. So right there, as they're moving at a high speed up the steep incline and then they stop, that means they're slowing down. That means at the beginning, we can expect the speed or the velocity and the acceleration to have different signs as they move forward. Then they go back down the incline backward. We haven't talked about what the signs of speed and velocity mean for something moving backward yet, so that'll be interesting. The engineer's data says that 2.5 seconds after beginning to move up the hill and accelerating at a rate of negative 8.2 meters per second squared, the train is still moving at a speed of 6 meters per second. We're going to determine the initial speed of the train at the bottom of the hill, how much time it will take the train to completely stop, and what the velocity of the train 5 seconds after it begins moving up the hill is. So, to start out, we know that the acceleration is negative 8.2 meters per second squared. We also know that over a time period of 2.5 seconds, the initial speed is unknown. That's the first thing we're looking for, but the final speed, the final velocity, I should be saying velocity here, the final velocity is 6 meters per second, 2.5 seconds after starting this acceleration. And that's a positive 6. So, since we know that the roller coaster train was moving forward, that means that since it was moving forward and the final velocity and the acceleration are opposite signs, the object must have been slowing down. The initial velocity is probably bigger than 6, and common sense tells us that as well. But let's solve for it. VF equals VI plus AT. VF is 6 meters per second, VI is unknown, plus our negative 8.2 meters per second squared multiplied by 2.5 seconds. Negative 8.2 times 2.5 is negative 20.5. I'm going to add that over to the other side, which is essentially like adding, so let's see, 6 plus 20.5. The initial velocity was 26.5 meters per second. Did the object slow down from initial to final? Yes, it absolutely did. How much time will it take the train to completely stop? Well, what does completely stop mean? That means, for the second part, that VF, the final velocity, is 0 meters per second. We now know that the initial velocity at the very beginning of moving up the hill was 26.5 meters per second. The acceleration hasn't changed. We're still dealing with the same hill, so that's negative 8.2 meters per second squared. The time is what we're looking for. The final velocity is 0, so I'm just going to cross that off and put a 0. So 0 equals, let's see here, 26.5 meters per second plus a negative 8.2 meters per second squared t. In order to solve for t, we have to move the 26.5 to the other side, so that's negative 26.5 equals negative 8.2t. I divide both sides by 8.2. And I find that t equals 3.23 seconds. So it takes a little bit longer than that 2.5 seconds in order to stop the train entirely. Now the last question might be the most interesting. What's the velocity of the train 5 seconds after it begins moving up the hill? You might think, well, wait a second. We need to maybe we need to switch things around. But it turns out this equation will work just as well, even if we have something that moves up and then starts moving back down the hill. We know that the time we're dealing with is 5 seconds. We're trying to figure out the final velocity. The initial velocity was, let's see here, the initial velocity was 26.5 meters per second, and the acceleration is negative 8.2 meters per second squared. Final velocity is what we're looking for. Initial velocity, 26.5 meters per second, plus negative 8.2 meters per second squared, times 5 seconds. 8.2 negative times 5 is negative 41. 26.5 minus 41 is negative 14.5 meters per second. Now what does that mean? What does a negative velocity mean? Well, all that means is that if the object was moving in the positive direction at first, now it's moving in the opposite direction. It's moving in the negative direction. And that makes sense because the roller coaster was going up a hill and then it came back down. So it makes sense that the velocity, if it's moving in the opposite direction, is now negative. Interestingly, it's now just like the acceleration. The acceleration and the velocity are now in the same direction. Let's see what happens at 6 seconds. Negative 8.2 times 6 plus 26.5, and we see that it's getting faster, okay? So interestingly, we see that if an object is moving backwards, positive acceleration would mean it slows down. Negative acceleration means the object speeds up. That's really important. Negative acceleration does not have to mean an object is slowing down. It could mean that you have an object that is speeding up instead. It depends on the direction of motion. If the velocity and the acceleration are in the same direction, an object will speed up. Its speed will increase. If the acceleration and the velocity are in opposite directions, it will slow down. Its speed will approach 0. The last question I want to do is a little tricky, okay? It doesn't involve any numbers. Two identical objects start from rest and are subject to the same acceleration. Object A is accelerated for twice as much time as object B. Prove that object A's final speed is twice as large as object B's final speed. So the equation that we're going to be dealing with here, again, is VF equals VI plus AT. We know that both objects start from rest, so that's going to be 0. So the equation that we're really dealing with here is VF equals A times T. For object 1, where for time for object 1 is just going to be our variable t, we get VF1, in other words, the final velocity of object 1, equals the acceleration multiplied by t1. So VF1 equals AT. Now, the reason I'm putting 1s as subscripts on here and kind of throwing some more stuff at you is because object 2 does not do that. For object 2, we have this. We have T2, or maybe I should put A's and B's. I'm going to change these. Instead of object A, we're going to call this object 2. Instead of object B, we're going to call this object 1. I don't know why I had it like this, okay? So object 2 is accelerated for twice as much time as object number 1. T2 is twice as big as the time for T1. If T1 is T, T2 is going to be 2T. That means twice as big. So the final velocity for object 2 is equal to the acceleration, which is the same, times T2. VF2 equals A multiplied by 2T. So VF2 equals 2 times A times T. Now look at what we had originally. Originally we had VF1 equals AT. I have an AT here. VF2 must be equal to 2 times VF1 because VF1 was equal to AT. What I've just done is I've mathematically proven that the final velocity for object 2 is twice the final velocity for object 1, which is what I was asked to do. You will see more of these proofs as we go throughout the year, but I wanted to show you the first one right now, okay? What we're essentially doing is working just with algebra instead of having numbers. This is actually much more powerful to deal with in physics, but you guys are just at the stage where you're starting to get the ability to understand this, so we're going to go slow with it, okay? Every once in a while, I'll show you something like this, more so as the year goes on. If you don't understand it now, that's fine. We're going to have plenty more chances to look at this, okay? Ultimately, what I want you to get from this is the idea of what acceleration is, a change in velocity over time, and how do we use it in problem solving. I'll be back to talk more about specific situations with acceleration. Bye.